Hello everyone. In this video we are going to talk about the pigeonhole principle. So we're going to try to motivate the pigeonhole principle here through a few examples. So the first one, this is just kind of a natural scenario / question. We have 29 students in our class. Must it be true that at least 2 share the same first initial? So of course you could look through the class roster and see, but without looking at all, could you guarantee that this is true? And the answer is yes, right? Because there are 26 letters in the alphabet and 29 people. There's no way that everyone can have a unique first initial, because that would mean there are at least 29 letters in our alphabet, right? And so this is a contradiction. And so in general, that's how one proves the pigeonhole principle. Let's do another example where we actually make this a bit more rigorous. Okay, so in this situation, we are giving out 10 pieces of candy to 3 children in a completely non-creepy way. It's Halloween or something. And we want to prove that at least one child gets at least 4 pieces. So how do we do this? Well, our idea here is to prove by contradiction. So we've got 3 kids, right? And so let A, B, and C be the number of pieces that the 3 kids get. So we know that these 3 things add up to 10, right? We're handing out 10 things. So we know A plus B plus C is 10. And if we try to prove this for via contradiction, we are going to suppose that A, B, and C are all individually less than or equal to 3, right? That would mean that no kid gets at least 4 pieces. And so what happens here? Well, if we know each of these is less than 3, or less than or equal to 3, then what is the maximum the sum can be? Well, this is like less than or equal to 3 plus 3 plus 3, which is 9. But then this is our contradiction, right? Because this says A plus B plus C, which is 10, is less than or equal to 9. But this is obviously impossible, right? So this is our contradiction. And so at least one of these is at least 4. And that would be our proof. So before we get to the general statement of the pigeonhole principle, I want you to think about this question. So again, we have 29 students in our class. How many can you guarantee for sure must share the same birthday month? Right, so kind of the highest number you can guarantee. And then I want you to explain your reasoning. So now we're ready for the general statement. So first of all, this is kind of an outdated reference because people don't really use, carrier pigeons to transfer messages anymore. But this works for anything where you're distributing something into different categories, okay? So if we have m times n plus 1 objects, these are our pigeons, distributed into n different boxes, the pigeonholes, then we're saying at least some box must contain at least m plus 1 objects. Right, so our previous example, what did we have? We had 10 pieces of candy, and then we had 3 kids. These were the boxes, right? And so m in this case was 3, n was also 3, and so this mn plus 1 is 10. That's how we saw that these 10 pieces of candy were into 3 boxes, and at least one of those boxes had to have m plus 1 or 4 objects, right? So how do we show this in general? I find it can be helpful to draw a picture. So if we have, box 1, box 2, down to box n, and let each of them contain, some number, call it xi for box I, then we want to show that there are at least m plus 1 if we start with mn plus 1, right? So we're going to prove this by contradiction. So suppose no box has more than m objects. Well, let's just translate this into math then, right? So we have xi in box I, this just says all of my xi's are less than or equal to m, right? So then x1, x2, etc. These are all less than or equal to m. Now we're distributing mn plus 1 things, so we know that these sum up. Just like the pieces of candy summed up to 10, these have to sum up to mn plus 1. But if each of them is less than or equal to m, then we also know that each piece individually being less than m, it means that, we're adding up n things no greater than m. This is going to be m times n. Well, this is a problem, right? We have mn plus 1 is less than or equal to mn. This is a contradiction, right? So this is exactly the same argument we just had. It's just, more general and not using these concrete numbers. And so there must have been one of them that had at least m plus 1. So let's look at an example. So here we're given 4 integers, and we want to show that there is some pair of those 4 integers whose difference is divisible by 3. So when you're starting these problems, you want to look at how many things are being put in, right? So we need to figure out how many boxes we need. So if we have 4, this is like our mn plus 1, and then we want some pair, right? And so our end goal is that we can fit m plus 1 in one of those boxes. And so this means that a pair, which is 2, is m plus 1. And so m is 1, right? Well, if m is 1, then this means n plus 1 is 4. So we know that n is then 3. So we're looking for 3 boxes to put these in. And the nice thing about this is that when you divide by 3, you kind of have 3 options when you're thinking about remainder, or mod 3, right? So you're either 0 mod 3, you're 1 mod 3, or you're 2 mod 3, right? You have remainder 0, 1, or 2 if you divide by 3. So if I have 4 integers, then at least some pair has to be in the same box. Now, why does this give me what I want? So if A mod 3 is equal to B mod 3, what does this mean? This means they have the same remainder. So this means like A is, say, 3k plus C, and B is also, some 3 times L plus C, right? They have the same remainder there. And so if I look at A minus B, what do I get? Well, I'm going to get 3k minus 3l, or 3 times k minus l, because the c's cancel. And so this is divisible by 3. This means that if I can fit 2 inside one of these boxes where they have the same remainder, then their difference will be divisible by 3. And so this is exactly what I have, right? So by the pigeonhole principle, I know that some pair has the same remainder. And I just proved that if they have the same remainder, then their difference is divisible by 3. Okay, so the trick is really to figure out how many boxes you need and how to define your boxes. Okay, so here we knew we had 3 boxes because we were able to solve for m in this 4 equals mn plus 1, and therefore solve for n, which is the number of boxes. And then using the fact that we have some notion of divisibility by 3 kind of naturally leads to these 3 boxes in terms of the remainder. All right, so for your second exercise, just to kind of practice this idea, a little more challenging one, suppose you have this set of 8 numbers, 1 through 8, and you are picking 5 distinct numbers from that set. Then explain why you have at least some pair from those 5 distinct numbers whose sum is 9. Okay, so you've got 5 that you're choosing, right? And you want a pair. So in this case, you want 4 boxes, right? Because if you have 5 things going into 4 boxes, then you want to fit in at least 2 into 1 box. So that's what the pigeonhole principle would say. So your real challenge here is to find what 4 boxes make sense for this problem. All right, thank you for watching.